Hello, everyone. I'm Juan, a PhD student at the Cox Group, and this is Perseus tutorial 2. So we will be starting where Carlo left. So first of all, it's also, so all the content is in your USB stick. So just open the folder containing, displaying the information, go to software, and then open the same Perseus version as you did for the first tutorial. And then we will load in the decision that was created by Carlo before. And to load in Perseus is extremely simple. So you just get the SPS file and drag it. And that's all. Okay, so everyone should have the same as I have now. So it finishes here, matrix 10. So maybe quickly check that the numbers are, some of the numbers are the same. So we are all in the same page. Okay, so what are we going to do in this tutorial? So the first part was data preprocessing and data cleaning, which is actually the most important part, because after, like from this, it depends all your further analysis. And in this part, what we want to do is to answer biological questions. So we want to transform our data into information, into biological information, to be precise. So the first thing I will do is I will copy the matrix, and like just for visualization purposes, I will create a second column with the downstream analysis. So just select that matrix, matrix 10, go to basic, and hit the little chip here, which stands for cloning. And this is basically copy pasting a matrix. So why will I do this? Then I will just select these two matrices and I will drag them to another column. Then I will reformat this a bit. So I will change exactly the layout so we can have more space for the plots and for the data. Exactly. So the first thing we want to do, because it's very useful for biologists and for people, yeah, exactly, for proteomic scientists and genetic scientists, is to visualize the differentially expressed proteins using a volcano plot. So the biological question we want to answer here is which proteins are differentially expressed in one cell type with respect to another cell type. So this is a two-sample comparison. To do this, you simply select the last matrix and click on the volcano plot icon. So the one that looks like a volcano, of course. So another window pops up, and then you have to select a few parameters. So of course you have to select a grouping because you have replicates. This is the only grouping we have, so we will left it. And then you have to select simply two different cell types. So we will stick with these two and click OK. Of course, you can simply choose whatever you like. Okay. Okay, so to visualize the plot, you just click on the test menu. Okay, so what can we see here? Exactly. So in the x-axis, you can see difference between EC and HC, right? So what this means is the difference in expression for a given protein between these two cell types. So 1 point is a protein, right? So if you click on it, you see what is the name of the protein. And then here, you will see the difference in expression for that given protein across the two cell types. And in the y-axis, you have minus the logarithm of the p-value, right? So like small p-values are well representative. So like what you want is small p-values, but what you have here is minus the log of the p-value. So like what you, like when you apply this transformation to a p-value, you will get that bigger values are actually representative of lower p-values. So this is basically, so like a point here is basically a p-value of 10 to the minus 6. So when you see 6 here, it's actually 10 to the minus 6. So this region right here and this region right here are actually it's actually a region with very high difference and with very small p-value. So these will be the proteins that are more significant, let's say. Exactly. So what this does is basically separates your data in two regions. So one below the curve and another one above the curve. And then these proteins right here, the ones above the curve, are the ones that are differentially expressed. Exactly. So let's do some, let's say, yeah, let's make it more clear that we have two different sets of proteins. So to do this, we will change the color of these proteins right here, the ones above, and also change the color of the ones below so we can visualize them easier. So this is very easy to do in Perseus because you can just sort your data by any column simply by clicking on that column label. So here. So exactly, I sort by significance, and then I want to select all the proteins that are above the line. So these are the significant proteins. So I just select the first one and then drag the list until the last one and simply press Shift and click on the last one. And then you can change the color simply by clicking on symbol color and choosing any color you like. I will take green. And then to show you that it is possible, I will also change the symbol type. So like by default, it's a square, but I want a filled circle. And then OK. And then you see that now the proteins that are differentially expressed are actually colored in green. And then to color the rest of them, you just click on the first one that is not differentially expressed, drag in the same way, press Shift, select the rest of them, and then choose another color. Exactly. Okay. So this is basically the volcano plot. Do you have any questions about its meaning or, yeah, something about this?
Sorry, can you just comment a little bit more about the S0 value?
Yeah, thank you for that question. So the S0 value is what Jürgen showed in his presentation of the Perseus basics. And the S0 is basically a term that accounts for variance, intrinsic variance of the experiment. So if you don't have this S0 term, I can simply change it here. So I click on the text box and write 0 and then recalculate. Then you will see that now your separation, like let's say your border is a straight line. And if you set it to, let's say 10, then you have a completely different region. So this term, so I mean, the statistics of a t-test is a ratio between variance, mean and variance, and then the 0 goes in the denominator as an independent term. So this is why you have this kind of hyperbolic shape, because it's asymptotically approaching. So like when this is very big, this is basically completely a straight line because you have an infinity in the denominator. So that's the idea. Yeah. Okay, now that we did
We have another question.
Yes, please.
And how can you decide which S0 value to use for your experiment? So you said it's an intrinsic variance, but how can we decide which is the best?
Well, it depends on what you mean with the best. So this is basically giving you a region in the p-value space for a given difference. So it depends on how strict do you want to be, right? So like if you set it to a very big number, you will lose most of the proteins. Mm-hmm. So I will just leave it the default unless I have a good reason to change it.
Okay, thanks.
Okay, sure. Okay, then yeah, maybe last question.
Other questions? Yes.
Yeah. So now that we saw how was a t-test for 2 samples, the next obvious step is to run a t-test for multiple samples. So to do this, you simply select the matrix again, go to test, go to multiple sample tests, and then this pop-up window comes up, and then you have to select the type of test you need. And this, so like the generalization to multiple dimensions of the t-test is called the ANOVA, or analysis of variance test, which is nothing more than exactly t-test in multiple dimensions. So we will leave the defaults and then click on OK. And then the software calculates or creates a new categorical column called ANOVA significance. And this column tells you which proteins are differentially expressed with from one cell type with respect to any of the other. So it's like now it's not like one-to-one comparison, but one-to-many comparison. So like if you have any match between two cell types, then you will get a plus sign here. Exactly. So why do you do this? Because with this, you can also calculate or do an enrichment analysis. And this enrichment analysis is called the Fisher exact test. So there are many ways of doing it. One way, one way I will show now, and the other one, if I have time, maybe I can show it at the end. But okay, I can actually, because it takes a little bit to run, I will run it now and then explain you what it runs. So you select the matrix, and because it's called a Fisher exact test, then you click on the fish icon from Fisher, and then leave categorical column. And because we want to build on our t-test information, you choose ANOVA significant, okay? And then click on OK. Okay, so it will take a bit, and I will tell you like more or less what are you doing here. So exactly. So the Fisher exact test is actually it's a measure of contingency, right? So, and contingency is another word for association. So what you want to see here is if you have a differentially expressed protein or a set of differentially expressed proteins, you want to see if this differential expression is associated with any annotation. So you want to see if the set of differentially expressed proteins actually show you that there is an enrichment or a depletion of a given annotation. So like this will tell you if a GO label or a KEGG entry is actually enriched or depleted in your data. Okay, perfect. So now we have the results. So like, where is the information if the annotation is enriched or depleted is here in enrichment factor. So the enrichment factor is if the enrichment factor is bigger than 1, then it means that the corresponding annotation, exactly, the corresponding annotation is enriched. If it is less than 1, then it's depleted. Okay, so this is one way of doing it. And now later we will see what is a better way of doing it. So now let's move forward and do some data visualization. So we will do PCA, principal component analysis. And to do this, we first need to only keep the proteins that were differentially expressed. So like we will only do it in this subset. So you select the matrix before the Fisher exact test, but after the multiple sample t-test, you select that one, -12, and you go to filter rows. And then you click filter rows based on categorical column. Exactly. And then in the column value, you choose ANOVA significant. And then you leave in values the plus sign. And then in mode, instead of removing, we want to keep the rows that are differentially expressed. So those with a plus sign. And then we click OK. So this is only filtering, so deleting the rows. So as you can see here, we have 3,406 items. And after the filtering, we have 2,584 items. Okay. So now that we filter our data, we will do PCA. So you just select the matrix and go to clustering PCA and choose principal component analysis and click OK. So it's very fast, and then you can already see your data. So you have 2 plots. One is at the column level. The one on the top is at the column level. The one on the bottom is at the row level, so at the protein level and at the replicate level. So of course, for this reason, because this is at the replicate level, you have 12 points. And what you can see here, if you select the points, let's say the point over here, then you know, or you read that it's actually the same replicates. So this is the use case of PCA at this point. So there are many use cases, but at this point, the most important use case, I will say, is simply to visualize if some of your replicates are very different, right? So here we see that that's not the case. So these all the replicates of the same cell type are actually like together in the protein space. Okay. Yeah, exactly. And then all the proteins, yeah. So different cell types are grouped together. So if you had, let's say, like if this point were actually instead of KC, HC, then you know you will have a problem because this is not, it doesn't make sense. So this is what, like one way of like you could use PCA for. Exactly. So that will be like the biological question we are answering now. So like, did I do something wrong with my data? Did something unexpected happen? Okay, and at this level is the protein. So like, as we can see here, it's like, so an axis will be a protein expression profile. So not one protein, but like a protein expression profile. And in this space, you have this massive blob in the beginning with like a few outliers. So one thing one can see here is, let's say, instead of this cluster, you had a huge cluster here and a small cluster here at in this area. Then you will know that something real is going on if that is not expected, because protein expression should only be so different if you are expecting it to be, or like if something biological process is going on the background. So here we don't see two clusters, so it makes sense because we're not expecting like two very big different. Exactly, we're not expecting a biological process very importantly disturbing the protein expression levels. Okay. So are there any questions so far about this? If not, then I will move forward. Yeah.
No, if you can further explain the above, the down graph, because the first one I understand,
Okay.
but the second one I didn't understand. Sorry.
Okay. Yeah, sure, no problem. Okay, so what you do in PCA, for those of you that don't know, is you take the matrix data. So you take this data only until here. You take this data and you calculate the covariance matrix. And then you do an eigenvalue decomposition, and then you truncate this matrix using to retain as much variance as you want. And then using, so like when you do the math, this new this decomposition actually gives you some principal axis in which you can plot your data from. So the idea is that the covariance matrix is diagonal in this space, okay? And then when you plot these axes, both x-axis and y-axis, are the axes in which your covariance your covariance matrix is diagonal, and means that are the axes with more variance. So these are the axes or the proteins that have more variance, let's say. So like in a very simple case, this axis right here will actually be the protein level, the protein expression of one single protein. But normally it's actually protein 1, the expression level of protein 1 plus the expression level of protein B plus the expression level of protein C. So it's like exactly a complicated function that makes your data more circular, let's say, in a way. It depends on what you did before. So if you normalize, you should expect it to be circular. If you did not normalize and nothing real is going on. So like, for example, one thing you could see here is batch effect. If you have that all the replicates in one batch form a cluster, and then all the replicates in another batch form another cluster, then that's batch effect. So this is the type of things you can see here. So you should expect that they are mixed. Exactly. Okay. Yeah, maybe last question and we move forward.
Sorry, I lost you at some point. The upper, you expect it to have the least number of proteins, and this would mean then that you don't have patch effect, right? Did I get it right?
I didn't hear,
Can you
sorry.
explain again the upper plot?
Oh, the upper
What you
plot.
expect from it?
Okay, okay, yeah. So from the upper plot, so this is at the replicate level. So you have 12 points because we have 12 replicates. Okay. So we have exactly. So what you expect here is that all your replicates are together, like geometrically together in the same space. If they are not, then something real happened. So this is at the quality control level. So if you see that there is a cluster of replicates here and another replicate here, then something real happened with that other replicate. This is what you see here. Okay. Okay, I will move forward. So now I will do clustering. For clustering, I first need to normalize my data. And because the type of clustering algorithm I will use, which is hierarchical clustering. So I just select the matrix and go to normalization and click on C-score. So C-score is calculating the mean of the whole data set and calculating the variance and then subtracting the mean and subtracting the variance and dividing by the variance, sorry. So at the end, you will have your matrix, your data matrix will have 0 mean and variance equals to 1. So this is what you are doing here. Exactly. So you should take no grouping here. Otherwise, you will be transforming your data differently, and they will give you wrong results. So no grouping, and then transform the rows, and then click on OK. So this is very fast because it's just calculating 2 values, and then it will give you a new matrix. Already, as you can see, the expression value changed. Let's take this one. So this one. Exactly. So it changed. And now we are in position to cluster our data. So we select the matrix, we go to clustering, we click on hierarchical clustering, and then this big menu pops up. And so it has a lot of options. So the most important one is this one, the distance hyperparameter. And this parameter tells you how are you going to calculate the differences, the distance difference between the protein types. So Euclidean is the normal Euclidean distance, of course, and L1 will be, for example, the absolute value. So this is very important because choosing different matrix will give you completely different results. So I mean, normally we use a Euclidean. So like if the use case is not very specific, it should work fine. Also the linkage. So the link, it's okay. So this parameter here is like related to how the algorithm works. So a hierarchical clustering algorithm, what it does is that it first calculates. So it takes all the samples, all the expression samples, all the samples, so the replicates and the proteins expressions, and it calculates distances between every pair of protein. So it creates a distance matrix, and then this distance matrix, you start merging together the closest points in this space. So you are creating clusters from individual proteins. So you take the 2 proteins that are closer, you merge them into a cluster. Then you do the same otherwise, and then when you have only clusters, you calculate the distance between clusters and merge the closest one. And how are you calculating the distance between 2 clusters? Using the linkage hyperparameter, right? So just leave it in average if you are not doing something very specific, and it should work fine. It's actually, for me, it's the one that works the best normally. And then you click OK. And then you have the new tab coming up, which is the hierarchical clustering tab. And there is a lot to see here. So first of all, there are 2 different clusterings. So one is at the replicate level and one is at the protein level. So as you can see here, so this is called a dendrogram. This representation here is called a dendrogram. So the dendrogram is merging first the replicates of the same cell type. So HC together, KC together, SC together, EC together. and then it's just merging the ones that are more similar. But if the algorithm was not seeing this, was not merging the clusters, their clusters in this way, that will be already a red flag. So this is yet another way to see if there is something real with your data. Let's say if it was clustering these two together, then that will be weird. Okay, and at the protein level, you have many clusters. So this is more difficult to interpret. I actually want to ask you if you have any idea what this will be useful for. So like what are, okay, actually a more concrete question. So here you can define a number of clusters for the proteins. Which number should I set here and why? Does someone have an idea? So like either what do they mean or like which number of cluster should I choose? If I set it to 4, what do you expect?
4 groups
And like what will this group mean?
in terms of behavior.
It tells you what, sorry?
Behavior.
Behavior.
Yeah.
Yeah, in a way. So what I will expect is if I set it to 4, I will expect a correlation between these protein clusters and the replicates, right? Because the cell type is defined also by the protein expression. So I just set it to 4 and let's see what happens. What can we see here? So first of all, look at this cluster, at this blue cluster. So this cluster is clearly here, has a low expression in this cell type, right? And let's say this close but has a very big expression on this cell type, right? So if you didn't have the labels of your, let's say if you cover these labels here, you don't know which cell types do you have, but you have the expression and the clustering, this will allow you to identify the cell type. Yeah. So there is a correlation between the clusters done with the proteins and the cell types. And I mean, and then this is up to a biologist or someone that really understands this data very well. So like, what else can I see here if I vary the number of clusters? So this is what I can see here is a way of identifying cell types based on protein expression, but you might see something different. Okay, so one way is like you could zoom in here simply by dragging this, and at some point you will have exactly the names of the proteins, and if you want to zoom out, you just double click, and what else? So you can select one cluster, and then it will give you a profile plot. But then the idea of Perseus is that, I mean, Perseus was built having ease of use in consideration. So like the idea is also like to play around with all of this. So exactly. So this will give you a profile plot where the color will tell you the distance from center in that given cluster. And if you wanted to, you could also do an enrichment here. So you simply exactly drag it up and then click on enrichment and then click on calculate, sorry, and it will calculate the enrichment eventually.